Typically, when you're being asked to balance a nuclear reaction, they're going to come to you in a format like this, where you're given a lot of the reaction, but there's going to be some unknown, which a lot of times is represented just by this X. So your job when you're balancing a nuclear reaction is to just fill in that missing piece. It's very different from the expectation that you would have if you're being asked to balance a regular chemical equation or balance a redox equation, where you'll be given products and reactants and you're trying to come up with stoichiometric coefficients. That's the goal there. When we're balancing a nuclear reaction, our goal is to find the missing substance, which is going to be in all of these equations. And to do that, we are just going to be remembering that these equations are all being balanced by mass. They're being, by mass number, and they're all being balanced by the number of protons. Now you're going to need to have a periodic table handy to do this, and I am just remembering that and getting one pulled up for myself. So let's get started. And this first one, for whatever reason, the subatomic particles are not written on the alpha particle. It's really helpful to write them in, even though we know what they are. It makes it easier for us to visualize and make some predictions about what this is going to produce. So now what we want to do is think about what is the mass number on the left-hand side of the arrow. We have 26 plus 1. That's a total of 27. And so that means on the right-hand side, we need to have that as well. We have 4 plus something, and that 4 plus something has to equal 27. So that tells us that for this X, the mass number is going to be 23. Has to be 23. And then now let's focus on our protons. For our protons, on the left-hand side, we have 12 plus 1, so that's 13. That means that on the right-hand side, we also need to have 13 as well. 2 plus what equals 13? That tells us how many protons we have. But we still haven't totally figured this out, because our goal is to figure out what X is. And this is where you're going to need to have your periodic table. Now remember that 11 is the identifier. That is what tells us the identity of the element. So you got to go to your periodic table and find element number 11. That is sodium. And because this is a nuclear reaction, it's normal for us to leave the 11 on the symbol, even though that's not what we would do in a non-nuclear reaction. So let's move on to the next one. Let's start with our mass numbers. On the left-hand side, we have 59 plus 2. That's a total of 61. On the right-hand side, we have 60. So that means that this particle, whatever it is, has a mass number of 1. So that the right-hand side also is 61. And for our protons, we have 27 plus 1 on the left is 28. 27 plus 1 on the right is also 28. So what is this guy? That is, you could either write proton like this, or you could write it as hydrogen like that. The next one is a little bit trickier because we have a stoichiometric coefficient in front of our X, but that's okay. We can still figure it out. So first thing we want to do is add up our mass numbers. We have 235 plus 1. That's a total of 236 on the left-hand side. So our right-hand side, we also need to have a total of 236. We have 94. And 139. So let's add that up. 94 plus 139 is 233. So that means that the mass number of all three of these X's is going to be 3 total. This is getting confusing. 236 minus 233 is 3. So each one of these particles has a mass number of 1. So that altogether they will add up to 236. 94 plus 139 plus 1 plus 1 plus 1 is going to be 236. And what about our protons? We have 92 on the left. And on the right-hand side, we have 36 plus 56 is 92. So that means that we can't have any protons in any of these particles right here. What is the subatomic particle that has no protons with a mass number of 1? That is going to be a neutron. So I hope you're getting the hang of it. Let's go maybe a little bit faster through the next one. So over here, our mass number is a total of 57, and our atomic number is a total of 26. So that means that this particle, 1 plus whatever, needs to be 57. So that means that our X needs to have a mass number of 56. And then over here, our atomic number is 26. 0 plus 26 is 26. This is definitely a big atom. We need to look at the periodic table and see what is 26. That's iron. There. Next one, we have on the left-hand side a mass number of 20, and on the right-hand side, we also need to have a mass number of 20. So this particle has to have a mass number of 0. On the left-hand side, we have an atomic number of 8, and that means we need to have an atomic number of 8 on the right-hand side as well. 9 plus what is 8? 9 plus negative 1 is 8. Go take a look at your list of the 5 subatomic particles. Which particle has a mass number of 0 and an atomic number of negative 1? That's our beta particle, or the electron. This guy down here, mass number of 135 on the left means we need a mass number of 135 on the right. So our particle has to have a mass number of 0. Atomic number of 53 on the left. Atomic number needs to be 53 on the right. 54 plus a minus 1 equals 53. So we got the same particle again, a beta particle or an electron. Mass number of 40 on the left. We need a mass number of 40 on the right. 0 plus 40 is 40. A mass number of 19 on the left. That means we need to have a mass number of 19 on the right. Be careful. Don't mess up simple math. Negative 1 plus 20 is 19. That's an atom. Look at your periodic table and see which one is atomic number 20. Atomic number 20 is calcium. When we're looking at these on the periodic table, all that we're focusing on is the number of protons. That is what dictates the identity of the atom. So we're paying no attention at all to the mass number when we're trying to match up the atomic symbol. 2 more to go. On the left-hand side, we have a mass number of 60. So on the right-hand side, we need a mass number of 60. 56 plus 4 is going to give us 60. On the left-hand side, we have an atomic number of 27. On the right-hand side, we have an atomic number of 25 plus 2. That is a helium or an alpha particle. And the last one we have here, another example with stoichiometric coefficient. On the left, we have a mass number of 236. So that means on the right, we need to have a mass of 236. And then on the left, we have an atomic number of 92, which means on the right, we also need to have an atomic number of 92. So let's start just by figuring out the total mass number and total atomic number for our X. I'm going to go, starting with the mass number, I'm going to go 236 minus 99 minus 135. That's going to be a total of 2. And since we have 2 of those particles, it's going to be 1 per particle. And now let's do our atomic number, 92 minus 40 minus 52. That's a 0. So 0 on that. And let's think about what particle that is. Something with a 0 protons and a mass number of 1. That is a neutron.